Kia ora. So far in this course we've focused on looking at solid objects and what happens to them movement-wise when we apply forces to them. One thing we haven't really thought about is the fact that a lot of objects are not solid like this. They can squash or flow in the case of a liquid. So we're going to move on to our new topic, which is to sort of understand how things like this behave. And in this video we're going to talk about elasticity, which is to do with objects that can be compressed or stretched. So we'll start off with a bit of an experiment, which is just to take a regular sort of household sponge as our prototype of material that can be squished, and see if we can understand what happens, or come up with a little mathematical description of what happens when we apply a force to it, like describe how much it will squash based on how much force we apply. So the basic setup of the experiment we're going to do is we're going to take a piece of sponge. I've measured it as being about 84 by 70 millimeters. Absolute precision is not really necessary for this demo. And we're going to apply a force to the top of our sponge and then measure the compression with a ruler. And you can kind of see the setup here in our picture. And we're going to use the scales to measure how much force we're applying and then see if we can figure out how that relates to the compression of the sponge. So first thing before we do that, we are going to, rather than talking about forces, clearly if you've got a piece of sponge, you need to apply a certain amount of force to compress it. If I had two pieces of sponges side by side, then I'd really need two copies of my hands applying the same force to compress it. So it's kind of, I'd need double the force to compress these two pieces the same amount, if that makes sense, one side by side of the same amount of thing. So rather than talking about force, we're actually going to use the concept of stress, which is a force per unit area. That way, it's the same stress required to compress this piece as it would be required to compress both of these together. So stress is defined using this Greek letter sigma, and it's defined to be the force that's been applied divided by the area over which it is being applied. And naturally the units are units of force divided by the units of area, so newtons per square meter is the unit we use for stresses. So for our example here, if we're going to measure 2 kilograms on the scales and we push down, then let's work out what the stress would be. Well, the stress in that case would be something like, so the stress is going to be the force divided by the area. The force in this case will be the mass times g, and our area is going to be, I think it was 80 millimeters by 74, so converted to meters, it'll be like that. Which will be 2 times 9.8, and we can work out what that's going to be using a calculator. Approximately 3,300 newtons per square meter. Okay, so you'll find these stress numbers are actually quite large, generally speaking, compared to your forces. That's normal. Right, so let's get into the experiment and see what happens, shall we? Alright, so I've got my scales zeroed off, and I'm trying to apply pressure to the sponge so that the scales read 1 kilogram. I'm trying to keep my pressure reasonably evenly spread across, and I'll read this value off the video afterwards so I don't need to try too hard. Now I'm going to increase it to 2 kilograms. Again, I'm just trying to spread that force as evenly as possible, and I'm going to keep going up to 2, then 3, approximately that is, and then keep on going up to 4. And I think my scales limit is 5, so I'll probably have to stop just before then. That's about 4. And a wee bit more. There we go, see how close we can get. Let's go for about there-ish. Sounds good. So if we collect all those results together, you can see I've drawn a table here. I've got my ruler measurement going down this column. I've turned that into a change in length from the starting position, because really we want to know how much compression there is, not the actual length of the sponge. So with no force applied, there's no compression, so that's 0. And all these other ones are just 21.5 millimeters minus these values, but converted into meters. Because remember, we have to convert all of our units into our standard ones. Then I've got my reading from the scales, converted that to a stress just like we did before, using my area and my value of g, and that's kind of what we do. And then if we plot these results on a graph, you can see that it forms pretty much a straight line. I've put the stress on the vertical axis and the compression on the horizontal. This seems a little bit backwards. Naturally you want to do it the other way around, but this is the convention that people use, and there is kind of a reason for this. So think of it as I'm applying a certain amount of compression and then figuring out how much stress was needed to do that, if that's an easier way of thinking of it. Okay, so that's cool. So we've got a nice straight line, and that would be almost enough to make a mathematical model. We could just come up with the equation of this line, and that would be all good. But we haven't really thought of everything yet, because what would happen if I added a second sponge and applied the same set of forces? So instead of having one sponge, I'm now going to have two. So the setup is going to look a bit like this now. In fact, maybe before we watch the video, have a think about what you think. If I apply the same amount of force, say 2 kilograms of mass on top of here, will I get the same amount of compression as when I had one sponge? Will I get more compression, or will I get less compression? Maybe you want to see if you can predict what that is before we actually move on and see what happens. 1 kilogram gets us about that much squish. 2 give us about this much. 3 gets me to about, oh, not yet, here. 4 around about here, and then 5, about the limit of what these scales can handle, is around about, you know, there also. Okay, so we've done exactly the same thing again. I have measured the compression, and I have collected those results again onto a graph. This time I have drawn on the same graph as my single sponge, which is the yellow one, and I have my double sponge, which is the orange curve, and you can see that for the same amount of stress, I get about double the compression. So if we look sort of horizontally on our picture, same amount of stress here gives me a whole lot more compression for our double sponge. And in fact, I mean, the relationship is kind of double up until about here, and then it goes a little bit different, but essentially, it's approximately double the compression for double the thickness. And if we were using an idealized version of the sponge, that would indeed be what we'd see. So what that means is that in order to come up with a mathematical description for how the sponge behaves, we kind of need to have a different one for every thickness of sponge. And that's annoying, because what we want to get at is some intrinsic property of the sponge that applies to any sponge that we can just figure out from its dimensions. So in much the same way as we used stress instead of force to measure how much force we were applying to it, we decided stress was a better thing, because that way we could sort of stop worrying about the actual area of it. In the same way, instead of measuring the absolute value of the compression in meters, we instead talk about a thing called the strain. And strain uses the Greek letter epsilon, and it's kind of like a percentage change in thickness. So it's the change in length, delta L, divided by the starting length, L naught. Okay, so we're basically going to start measuring strains, or calculating the strain instead of just the compression, delta L. Okay, so L naught is the unstressed thickness, and what we should hopefully find, given the graph we saw before, is that no matter what dimensions your sponges are, whether it's this one, or a whole stack of them, then the same stress ought to give the same strain. Okay, so let's see what happens if we take the same graph we did before and instead look at stress versus strain for both experiments. So here are my results, and again you can see instead of having delta L, I've added an extra column of strain, which divides by the original length. Oh, other thing I should say, strains do not have units, because the units would be meters divided by meters, which is just what we call dimensionless. So you can see I've got my strains, and I added in my extra little entry for my length here in my spreadsheet. So there are my strains for the two experiments, and if we just draw stress versus strain on the same graph for both of them, you can see that more or less these two curves have the same slope. Okay, they're almost the same line. They're a little bit different just because there are some imperfections in my experiment and in the sponge. But essentially, the two curves have come together and they're largely speaking the same graph. So that's cool. So that means that no matter how thick my sponge is, I can determine its compression by looking at the stress versus strain model, which is a straight line. So the slope of this line has a special name, it's called the Young's modulus, and we usually use the symbol Y, although occasionally you'll see people use the symbol gamma for this. Kind of looks quite similar, but that's a Greek letter because we like Greek letters. And the unit for this slope is also newtons per square meter. Another name for this is pascals, and so you may sometimes see Young's modulus stated in the units of pascals. So for a linear elastic material, which is sometimes called a Hookean material, what it says is that the stress is just the Young's modulus times the strain. Or alternatively, we can work out the Young's modulus from the stress divided by the strain. And this is just the equation of this straight line here, which we've assumed is going through zero. Zero stress should mean zero strain. And if the Young's modulus is higher, so if we draw on the curve for a substance with a higher Young's modulus, so a steeper curve, what that means is to get the same amount of compression or the same strain, you have to apply more stress. So if you've got a higher Young's modulus, that means your material is stiffer, it is more resistant to being compressed. If you've got a lower Young's modulus, then your material is easier to compress. Okay, maybe a helpful way of remembering how some of this works is we discovered with this experiment that the same force compressed more in absolute terms, but the same strain. So I kind of think of the princess on the stack of 20 mattresses. If you put a mass on a very tall object made of your substance, it will compress quite a lot, but the strain is the same. Okay, so Young's modulus, that is a property of the material that you're studying. And then you just grab the dimensions, which is like the thickness and the area, to relate the force and the compression together once you know this Young's modulus. I've just talked about one particular type of stress that we can apply to an object. We've just been considering stresses where we're applying a force to both ends. Okay, the force from the bottom is the reaction force from the table or the scales in my experiment. And my stress, so here's my stress, which is sigma, is my force divided by my area. And then I had my strain, which was delta L over L naught. And then when I squish it, maybe it comes down a little bit, and then I got a change in length, delta L. Okay, now that's called compression, but like I said, it's not the only kind. We can do a very similar thing when instead of pushing down on it, we're kind of pulling it apart. We're kind of stretching it out. So again, if we've got this area here, same area, and the same, this same symbol, it's still a stress, but it's called a tensile stress rather than a compression. So if we apply a tensile stress, what will happen is that our object will stretch out a little bit. The thickness will increase by an amount delta L, and we're still going to start off with the sort of starting length as our equation. And Young's modulus applies here as well. So we'll still get that the stress is going to be Young's modulus times the strain. Same with here. Stress is Young's modulus times the strain. And in both these cases, the strain is delta L divided by L divided by L. Now there's one other kind of stress which is a bit weird, and this is what we call shear stress. So you imagine your object sitting on the ground and you're kind of pushing that way on it. And what that will make it do is kind of do this shear movement, which is kind of turns your cubey type thing into a parallelogram type thing. So if I'm applying a stress kind of this direction, and there'll be a corresponding one from the ground here as well, same area on top here, then that's called a shear stress. And this is not governed by the Young's modulus, so we're not going to talk too much about this right now other than to mention that it exists. And in this case, the dimensions are a bit weird. This one is the L we use, but the delta L that we use, the change in length, is that one there. So again, once again, the stress will be whatever this force is divided by the area, but the strain is going to be delta L divided by L naught, as illustrated in this picture. And they have a similar equation, but it's not the Young's modulus that defines it. It's a thing called the shear modulus. Like I said, we're not going to really go into that too much, other than to mention the thing we need to consider. And finally, there is actually one other type, well, there are a couple of other types, but one other type that I'll mention. Another kind of way that we can deform a solid is by twisting it. Okay, so I grab my sponge and I twist it around to try and wring it out, and that's called torsion. So also torsion, which is a twisting. So let's just make a couple of comments about the Young's modulus. So when we've got a small amount of stress on an object, we tend to find that the stress is directly proportional to the strain, i.e. we get that straight line relationship we just talked about. And just to emphasize again, for compressive or tensile stresses, those are the squishing or stretching stresses, that's when that behavior is governed by the Young's modulus. And we can see that the Young's modulus is given by the stress divided by the strain. And for most materials, you get a very similar Young's modulus depending on whether you're squishing it or whether you're stretching it. And so generally speaking, these two values will be approximately the same. But when it comes to biophysics, one notable exception is bone, which has a higher Young's modulus for tension or stretching than it does for compression. But these are properties that can apply to bone, and so we could, for example, use those to make some kind of calculation. Before we finish up, it's worth also mentioning a couple of non-ideal examples, because obviously if I keep pulling harder and harder and harder, at some point in time this is not going to just stretch like a nice spring or rubber band, it's going to tear. So there's going to be some non-ideal properties going on here as well. And also we should relate this back to something that you might have done before, which is Hooke's law for springs. So you may have come across before that when you've got a spring, that the force is equal to the force applied to a spring is equal to the spring constant K times the extension delta X. And this will apply to like a rubber band or a spring or something like that. This is basically the same thing as we've just been talking about, because if you look at our sponge experiment, we had that our stress is equal to the Young's modulus times the strain, but our stress is just our force divided by area is equal to Young's modulus times, I'll call it X instead of L now, but same thing, right? So stress, force divided by area, is equal to Young's modulus times strain, which is change in length over starting length. And if I rearrange this slightly, I get F is equal to A y over X naught delta X. And so this here, that is my spring constant. So I can turn it back into an equation relating the compression and the force, and you can see that what that's done is basically I've just included the dimensions of my substance, and then now I have an equation relating force and compression. But the nice thing is this Young's modulus, this was a property of, in my case, sponge. So if you gave me a sponge of a certain set of dimensions, I could work out this spring constant, if you like, by plugging them into that relationship there. Okay, so like I said, not everything is ideal. We said for small amounts of applied stress that we get this linear relationship. So that's what we call the elastic region of the material. Okay, so what you're imagining here is that we're taking our thing and we are pulling it harder and harder and harder to stretch it out to a certain length. So what happens is if we keep on pulling, then suddenly we get into this region where up to a certain point, when you pull a bit harder, it actually gets a bit easier to make it go further. It's because your material is starting to break down. And that's called the plastic region. And it won't recover its shape once you've started stretching things into the plastic region. So when you let go again, it won't spring back down to zero because you've done some sort of fundamental molecular structure changes to it. Kind of like a balloon that's been blown up really hard and it comes back kind of a bit different. And then if you keep on going, then essentially it's going to let go and then it's going to break. Okay, so if you keep on past a certain point, it suddenly gets a bit easier again to keep on extending it out, and then it breaks. And so the highest amount of force that you had to apply as part of that process is called the ultimate strength of the material. And then the breaking point is obviously the point at which suddenly it tears or rips or something and you no longer have your piece of solid anymore. We're not going to worry too much about this other than to mention that not everything behaves like this all the time. There are limits when you go beyond that where things will behave a bit differently. And not everything behaves exactly like that last one either. So when, for example, you look at a ligament in biophysics, you get quite a weird stress versus strain behavior. Because initially, when you start pulling it out, it stretches out really easily. That's because the fibers are kind of crimped together in a certain way inside the ligament, and the initial part of sort of extending it is just kind of uncrimping the fibers rather than actually stretching them out. So that's called the toe region, where it's quite easy to extend it initially. Then when you try and extend it a bit further, that's where you get this linear part of behavior, which again is that stress versus strain relationship we talked about before. And then there's the yield region where you're basically injuring it and it damages and breaks, okay, which we want to avoid doing for our ligaments if at all possible. Okay, so we'll do a couple of examples of these problems in a separate video, so we'll call it quits here. Ka kite anō.